In this video, we will be learning state variable models. State variable models are a state space representation of physical control systems. They form the foundation of modern control theory. This slide outlines the topics to be covered by this lecture. First, I will review modern control theory in comparison with conventional control theory. Then I will be introducing a number of state space related definitions. After that, we look at the state differential equation of LTI systems. LTI stands for linear time invariant. Then we move on to the solution of LTI state space models. I will also explain how to link a state space representation with a transfer function. Given a transfer function of a physical control system, in theory, there exist infinitely many state variable models, all of which describe the same system. We are interested in concentrating on a number of special formats. And these special formats of state variable models or state space representations are called canonical forms. In this subject, we will be learning 3 canonical forms. And the 3 canonical forms are shown by the last 3 points on this slide. Now let's look at the comparison between modern control theory versus conventional control theory. Conventional control theory is based on the input-output relationship of a control system. And we know that the transfer function model captures this input-output relationship. By contrast, modern control theory is a time domain formulation, and it is based on a state space representation of physical systems. Conventional control theory is only applicable to LTI systems. However, modern control theory suits a wide variety of systems. The systems may be linear or nonlinear. They may be time invariant or time varying. We know that a modern complex system may have many inputs and many outputs, and this type of system may be called a MIMO system. Because a state space representation is a time domain formulation, it is best suited for programming using digital computers. That's why modern control theory plays an important role in studying physical control systems. Now let's look at a number of definitions which are closely related to a state space representation or a state variable model. The first definition is state. The state of a dynamic system is defined to be the smallest set of variables, which are called state variables, such that the knowledge of these variables and the input completely determines the system behavior. For example, if we have a third-order system, that means we should have 3 state variables, and they are called x1t, x2t, and x3t. Remember, a state space representation is a time domain formulation. Therefore, all the state variables should be functions of time t. The number of state variables describing a state variable model should be equal to the system order, and the system order is equal to the highest order of the characteristic equation, which should be the denominator polynomial of the transfer function. Now let's look at the second one, state vector. The state vector is a column vector whose components are state variables. So if we stack up all the state variables into a column vector, this vector is the state vector. And I'm going to use xt with a tilde under it so that it means it is a vector. So this is the state vector of a third order control system. This state vector contains 3 state variables. The last definition on this slide is the state space. The state space is the n-dimensional space consisting of the n-axis. Each axis represents a state variable. Any state can be represented by a point in the state space. This point represents a state in this 3-dimensional state space. The response of a control system represented by a state variable model can be computed given the state variables of the system, the input, and the state space representation of the system. So now this system is represented by a state space representation. A state space representation is a first-order vector matrix differential equation in the form shown by this. It consists of 2 equations. The first equation we call the state differential equation, or simply the state equation. And the second equation we call the output equation, OE. If we concentrate on the first equation, you see that it is a first-order differential equation in the matrix form. X dot t and I use tilde to represent it is actually a vector. X dot t simply means x1t dot x2t dot xnt dot. The dot means it is a first order derivative. Therefore, for a general state variable xit dot, it is simply the first order derivative of xit with respect to t. You will also see 4 matrices AT, BT, CT, DT. These matrices are called the parameter matrices of the system. And you can see in this description, these matrices are a function of t. So the state variable model shown on this slide is actually a linear time varying system. On the bottom of the slide, you will see a generic block diagram that shows the signal flows of this state variable model. Now let's review the definition of time invariance. A system is said to be time invariant if the response to a time-translated input is simply a time translation of the original response. That is, if the input to a system is a time-shifted version of the original input, then the time response of such a system should also be a time translated version of the original response, and the amount of time translation should be equal to the time shift of the input. Now let's have an example of an RC circuit. We know that the input to this system is a voltage source, which is represented by the signal E of t. The response of the system is shown by this graph. Now, if we excite the system with the same input, but the input has a time delay of tau seconds, then what type of response do we expect? The response is exactly the same as the previous one, but it is a time delay version of it. So this is the time invariance property of a system. Now let's look at the state space representation of LTI systems. As I mentioned earlier, a state space representation can model a multi-input, multi-output system. So now if we have an LTI system with R inputs and M outputs, it has n state variables to describe the system. Then the state space representation of this system is given by these two equations. We know that the first equation is called the state equation, SE, and the second equation is called the output equation, OE. If you observe carefully, you will see that for an LTI system, the parameter matrices A, B, C, D now become constant matrices. And that's because it is a time invariant system instead of time varying. So now the question I'm going to ask you is, can you tell me the dimension of the matrices A, B, C, and D? In this state space representation, we know that xt is an n by 1 column vector. And because the system has m outputs, yt should also be column vector with m elements in it. So the dimension of yt is m by 1. And the system has r inputs. So the system input ut should also be a column vector, and it has r elements in it, represented by ut, this column vector of size r by 1. Now you should be able to specify the dimensions of A, B, C, and D. Always remember matrix A is n by n. So matrix A is always a square matrix, and dimension of it is equal to the dimension of your state vector. A is n by n. What is the size of B? B should be n by r, because the system has r inputs. The dimension of C should be m by n, because the system has m outputs. The dimension of D should be m by r. I have put a document about matrix operations in the useful material folder so that you can get yourself familiar with basic matrix theory. The dimensions of A, B, C, D are easy to work out as long as you have some basic knowledge about matrix operations. if the system is a single input, single output system, which we call a SISO system. For a SISO system, your matrix A is still n by n. It's always a square matrix. Matrix B becomes a column vector with n elements in it. Matrix C becomes a row vector. It is 1 by n. Matrix D, in the SISO case, becomes a scalar. Therefore, it is 1 by 1.